good day. So, in this third lecture we will be looking at physical medium. Now, whatever in the last lecture we have seen two protocol stacks. We have seen OSI protocol stack in details, and just we had a look at TCP/IP reference stack. But whatever be the model, at the bottommost layer you have the physical medium, because after all if you have if the two computers are to communicate, then there has to be some physical medium between them. So, we will just look at some general characteristics of physical medium and how data can travel along them today, and in the next lecture we are going to look at some specific media which are used in networks. Okay. Now, as we talk about the physical medium, we have to talk about two different modes of communication. So, to say one is analog and the other is digital. So, you have before you this the top one is the analog signal. You can see that it can take sort of any shape, and the digital signal some square wave kind of signal. All right. Now, actually this digital signal really represents a series of ones and zeros, a stream of bits. So, but analog signals of course can take any value in general. Okay. And one important consideration for any medium is that what it is bandwidth. Bandwidth is the capacity of a media to carry information. Now, the total capacity may be divided into channels. I mean, there is one total capacity, you can sort of divide it into channels and give different channels to different users, and you can do things like that. Of course, a specific portion of the channel may not be used for direct communication, but for control purpose or for other specific purpose, etc. But whatever it is, any particular medium and technology will have a certain capacity, okay, and this is very important, because after all your speed of communication would depend on the capacity of the media. So, and this inherent capacity of the medium is of course intermittently linked with the kind of signal a particular channel can carry. For example, this is on the left hand side you see some digital signal, okay, and just on its right actually there are some kind of bar graphs. It looks like a bar graph actually. So, this is a representation of the same signal in a different way. What this right hand side says is basically you have if you have a series of a sin x plus b sin 2x plus c sin 3x plus d sin 4x and so on, okay, where a, b, c, d represent the values shown by the graph on the right hand side. If you sum all that sine functions up, you will get the signal on the left hand side. Okay. So, the channel, if it has to carry the digital signal, has to be able to carry all these so called harmonics. Harmonics means this sin x function, this sin 2x function, sin 3x, etc. So, all these harmonics it should be able to carry. Whereas, in the second figure B, if you look at it, it is a pure sine wave. So, it is just it has got one harmonic, it is some a sin x, something like that. The third figure is two harmonics, say a sin x plus b sin 2x. Okay. So, depending on the complexity of the waveform that you want to carry, you need more and more bandwidth on the more and more bandwidth for the channel. Okay. Now, for this we make a comparison here of analog versus digital signals. All right. Now, digital signals have some very basic advantages. The most basic advantage is that it is less error prone. That means, even if there is some kind of distortion in the signal between the source and the destination, that can be rectified very easily, and to a limited extent errors can be corrected. Whereas, if you are talking about an analog signal, there is little control over signal distortion. Of course, this is also old technology, and as I mean this has got some limitations in technology, in the sense that how many people can use, etc. There are some limitations over here. So, digital signals are, of course, in general are preferred, although analog signals still rules in some niche areas. So, let us see what we mean that by the statement that digital signals are less error prone. So, in this figure we see on the left hand side we have some analog signal, and then some noise has come, that means some distortion has come, and the signal looks like the one below. So, when noise affects an analog signal, it is hard to deduce the original signal from this. Whereas, the same kind of noise, similar kind of noise, if it gets superimposed on a digital signal, as you see on the right, okay, the signal gets distorted, but since we know that the original signal was sort of square shaped, we can deduce the original signal from the distorted signal. So, the so despite the noise, so the noise can be eliminated easily in digital communication. So, that is the greatest advantage of digital communication. And so far as the bandwidth of a channel is concerned, suppose we know the bandwidth h of a channel and the number of signal levels v being used, what is the maximum number of bits that we could transmit? Suppose we are trying to transmit say bits in terms of digital signal. So, there is a Nyquist limit which says maximum bits per second is 2 star h star log base 2 v. So, for example, if the bandwidth is 3100 hertz and we are using 16 level modulation, then maximum number of bits per second is, so log of 16 to the base 2 is 4. So, 4 into 2 into 3100, that is 24,800 bps or 24.8 kbps. So, this is the maximum number of bits that we can send through a channel of this particular bandwidth. So, the higher the bandwidth of the channel, the higher the number of bits that we can send through it, but depending on the bandwidth, there is always a hard limit on how fast we can communicate. So, let us look at this digital regeneration of digital signals once more. Okay. So, we say that it is reliable because it can regenerate slightly damaged signals. Since there are only two states, for example, this is the original signal which is a square kind of thing, which is grossly distorted as it is received. Okay. This has become weaker in strength, and the shape has also been deformed, but we can regenerate it, since we know that the original shape of the signal must have been a square one. So, we regenerate it as a square one. So, if there are two states of voltages, let us say plus 10 volts and minus 10 volts, and the signal is plus 8 volt, let us say, then it is quite possible that this plus 8 volt is a result of noise which is superimposed on a plus 10 volt, rather than a result of noise superimposed on a minus 10 volt. So, whenever you get plus 8 volts, simply make it 10 volts with some electronics, and the original signal will be restored. Of course, I mean if the noise is very high, and I mean there is a limit to this how much you can restore. If the noise is very high, then it will not be possible, then we will know, because the minus 10 volts can also become 8 volts, say if in case of a spike, and then whatever restoration we do will be a wrong one. So, we will lose some information, there will be some distortion and some loss of information would be there, that is there. So, there is always a limit, but in the case of digital signals, it is more fault tolerant or resistant to noise, more resilient compared to analog signals. Okay. So, we can correct errors in transmission, that is another advantage of digital signals. So, what we do is that we add a few bytes of error checking information and can ask for retransmission if an error is detected. I mean, I will give you a simple example. For example, suppose we are sending groups of 8 bits called bytes. Okay. Now, what we can do is that associated with each byte we can add an extra byte, and this extra byte would make the, let us say, the number of ones in the whole 9 bits to be odd. Okay. This is an example of, let us say, odd parity, so called odd parity. Now, if at the receiver end we find that the number of ones have become even, we know that there must some bit must have flipped. That means some bit must have, instead of a 0 we got a 1, or instead of a 1 we got a 0. It must have happened otherwise, because the number of bits was supposed to be odd. And of course, by adding one bit we can always dictate that the number of bits in the original, that means sending station, was odd. So, in that case the receiver may request the sender to retransmit that whole bunch once again. Hopefully there will not be a error next time. So, some kind of so this is of course a very primitive kind of error checking. There are more sophisticated error checking which is employed in networks and communication. So, this such error checking and even correction of errors at the receiver end, if you are adopted a very sophisticated coding technique. So, that is possible in case of digital transmission, which is not possible in analog transmission. Another advantage, and this is becoming more and more important these days, is that a digital signal can be encrypted. All right. So, this makes it possible to carry on sensitive information on the network. For example, nowadays e-banking is coming in vogue. That means somebody does a bank transaction on the network. Similarly, e-commerce, that means you want to buy something online and then pay through your credit card, etc. online. Now, how does the transaction take place? The point is that you are after all sending some information, maybe your credit card number, maybe some password, etc., etc. Now, if somebody can snoop on you in between, so they will know your secrets, and then they can use the same set of numbers to maybe buy something else, and the money will go from your bank account. So, that is obviously not acceptable. So, in this case, when we send it down the network, we encrypt it in a way, so that even if somebody snoops and finds out the stream of bits that is going, he will not be able to make out the original numbers from this current stream. So, this is encryption, and this is got very important applications these days. So, encryption was another advantage of digital transmission. Compression is another. That means we can compress a message before transmission and decompress it at the other end. So, the overall load on the circuit, overall load on the circuit and the network is lighter. So, sometimes it is, so that is why since the load is lighter, it is also less expensive. Sometimes of course, when you compress some information, there may be some loss of information. There are lossy compression techniques and there are non-lossy compression techniques, okay, loss-free compression, lossless compression techniques. If it is a lossy compression technique, you may lose some information, but it may not matter. For example, let us say you want to send a digital photograph. Now, a digital photograph may have a very high resolution. If you compress it, and on the other end you may lose a few bits, but your the image that you get on the other end would still look almost as good. To untrained eyes, it will look almost as good as the original one. Of course, trained persons can look at it and find out that okay, there is some things missing, but it will serve for most purpose. So, sometimes even lossy compressions are acceptable, and of course, there are lossless compressions also. So, when you compress it and send it, there is I mean, it is a less expensive way of sending the, I mean, you are sending essentially the same information, only you are taking less amount of space. Okay. Of course, you have to do the compression and decompression at the two ends. So, that is somewhat some kind of overhead on the two sides. Okay. Now, suppose we have some data, how do we encode this digitally? Well, the simplest way of course is to by the presence or absence of a signal. Okay. Let us say a positive voltage might represent a binary 0 or a binary 1 or vice versa. Okay. So, maybe if you have a high voltage, you say that okay, I will interpret this as a 1 being sent, and if I have a low voltage, I will interpret this as a 0 being sent. Of course, when I am saying voltage, I am assuming that we are having some kind of electrical signals is travelling. That is not always the case. For example, in the if you are using light for communication, the presence of light might indicate a 1 and the absence of light may indicate a 0. Okay. So, whatever way you code it, whatever be the medium, so this is the simplest way to encode data into a digital form. So, the current state indicates the value of the data. Now, analog transmission. This is analog transmission. Of course, if your signal is digital, I mean sometimes you are forced to send some digital signal by analog transmission, but this is usually not preferred. Okay. So, of course, analog signal will transmit whatever signal comes regardless of whether it represents digital or analog data. So, it uses amplifiers, but the trouble with amplifiers, I mean rather than the kind of regeneration that is possible in digital world, the trouble with amplifiers is that it also boosts noise, whereas in the digital case we could I mean take out the noise and regenerate the original shape of the signal. Here we can amplify it, so that if the signal becomes weak, we can make it stronger, but whatever noise is coming with the signal, that also gets amplified. So, but this is okay for voice, but for digital data using analog transmission usually is not done, because we have so little control over the correctness of whatever we are sending. Now, in digital transmission, this is concerned with the content of the signal, uses repeaters which recover the pattern of zeros and ones and then retransmits. This can be used with analog signals if it carries digital data. Okay, you know, sometimes analog signals would carry digital data. It recovers the digital data from the analog signal, generates a new clean analog signal. Okay. This is becoming more standard. For example, I will give you an example. For example, when you are connecting to the network, and many of you may have done this, when you are connecting to the internet from your home computer, you might have used a modem, okay, and a telephone line. Now, so what is happening over here is that the telephone line is essentially an analog medium. So, an analog signal will go over there on that, but your whatever is coming out of your computer is digital. So, what you do is that you make this digital data ride on some analog signals through this modem pairs, etc., so that it reaches the telephone exchange. At the telephone exchange, of course, it is converted back to digital data, and the backbone and the core of the telephony system is purely digital nowadays. So, we will come to that when we discuss telephone systems. So, there are various ways in which you can encode digital information in the analog domain. One is the amplitude shift keying, okay, which means that two binary numbers 0 and 1 represented by two different amplitudes of carrier waves. This is not very efficient and used up to 1.2 kbps on voice grade lines, and used to transmit digital data over optical fiber. That is of course always there. So, in the amplitude shift keying is very simple. Although the signal is analog, we know that there are only two levels which this signal is supposed to take, the two amplitudes. Okay. So, maybe low amplitude and high amplitude, it may be even 0 and some amplitude, alright. So, if 1 is to be transmitted, maybe we give this high amplitude, we send a high amplitude analog signal. If 0 is to be transmitted, we send maybe a low amplitude analog signal. Okay. You might say this is the kind of thing which is done in the optical domain, alright, but in the electrical domain this is not very efficient. More common is the so called frequency shift keying, and in frequency shift keying we use the two binary, and that means we use two different frequencies for the two binary digits 0 and 1. So, this is less susceptible to error than amplitude shift keying, and again it sends up to 1.2 kbps on voice grade lines and commonly used for high frequency radio. Another way of encoding is the so called phase shift keying. Two binary numbers may be represented by phase shift of a carrier wave. So, this is more efficient and noise resistant than FSK. So, this PSK. So, it can be used for up to 9.6 kbps kilobits per second on a voice grade lines. For this is for simple phase shift keying. Of course, we use more complex phase shift keying with other techniques in order to achieve even higher data rates nowadays. So, these techniques can be combined. So, it is common to combine phase shift and amplitude shift keying. So, we can get about 56 kbps on a voice grade line. So, this is the so called 56 kbps modem, sorry, that should be 56 kbps rather than kps. So, this should be you can get 56 kbps on a voice grade line, and this is very common these days. So, the modems that you buy, they all usually they are all 56 kbps kind. With some techniques called multi-level signaling, each signal represents more than one bit, alright. So, this is also possible. One is the signal which indicates the level of the voltage or whatever it is, phase, frequency, whatever it is, that is the level of the signal. The other is the bit or bits that it may represent. So, so these two are actually, I mean, sometimes, for example, if you have a simple, if you represent the 0 or a 1 by the current level of the signal, which is the simplest kind of technique, there these two are the same. So, one is the bit rate, that is the number of bits of information that you are sending, other is the baud rate, that is the number of times the signal will change per second, maximum number of times the signal will change per second. Okay. So, in the simplest case baud rate and bit rate may be the same, but that is not always the case. So, we look at the other side of the coin, which is the digital encoding of analog information, and a very common case is the telephone. For example, as I just now told you that the heart of the telephone exchanges and the telephone switches and the trunk exchanges and the core network of the telephone system, they are nowadays entirely digital, whereas our voice is of course analog. By the way, the real world that we move around in, that is mostly analog. Okay. Now, this digital is something that we adopt in between in order to get these advantages of robustness, resiliency, this error correction, etc., etc. So, our voice is analog, but the core telephone system is digital. So, at some point our voice, this analog signal has to be converted to a digital signal. Of course, our handset mostly, they are also mostly analog. So, they are going to be carried maybe in this analog fashion right up to the nearest exchange, but there will be a set of codecs, so called coders and decoders, which will convert the voice, this analog voice signal to a digital signal. Now, what kind of digital signal will a voice give? The calculation is something like this. So, voice data in telephone system is limited to a maximum of 4 kilohertz. Okay. So, this is not, I mean, a telephone, this is a very good quality voice, so called toll quality voice, but this is not a high fidelity kind of sound. Okay. So, it is less than high fidelity, but very clear. So, for all practical purposes for the telephone at least. So, if I limit the bandwidth to 4 kilohertz, we get some distortion, but nothing very noticeable. So, voice is still very clear. So, we have to send this 4 kilohertz of analog signal, this 4 I mean whatever information is there within this 4 kilohertz bandwidth, we have to send this analog signal to the other side in a digital form. That means, we have to digitize it. Now, there is a so called Nyquist rate which is there, just we have seen Nyquist limit just some time back. So, this Nyquist rate which says that if we sample any analog signal at double the maximum frequency that particular analog signal has, then essentially we will have all the information that is needed to fully reconstruct the original analog signal from these samples. Okay. So, if we have 4 kilohertz of signal, 4 kilohertz of bandwidth, so we require 8000 samples per second. So, we require 8000 samples, that means per second this whatever let us say you have this analog voice. So, per second we will take 8000 samples, sample values at different points, 8000 of them, all right. And these 8000, so of course, at some point my voice may be low, so I may have a very small amplitude. At some point my voice may be very high, so I can have a large amplitude. So, we have such 8000 samples. Now, what is that each of these samples we break it up into a code of 8 bits. Okay. So, the point is that with 8 bits you can really distinguish between 256 levels. So, and our assumption is that from the 0 level to the highest level that is admissible, or we take it whatever it is, if we break it up into 256 parts, that is good enough for capturing how high or low the volume is. So, 256 levels is really quite a lot. So, we require 8 bits for each of the sample, and we require 8000 samples. So, that makes it 8 into 8, 64 kilobits per second. And as a matter of fact, please remember this rate 64 kilobits per second. This is the fundamental unit on which I mean on which a whole lot of all other technology etc. Has been built on this. And basically it has come this way precisely from telephones, because the telephone people had the first network, and 64 kbps happened to be the rate which is for a voice. So, naturally now of course, if you want to carry one voice channel, so we will have one such 64 kbps. If you want to carry 1000 voice channels, so you will require 64 kbps into 1000, that is 64 mbps capacity. So, they plan their network that way, depending on how many voice channels they want to carry where, but 64 kbps is the basic unit in most places in telecommunication. Now, let us take a quick look at how data is encoded. So, one is of course using the simplest one is of course using the level of the voltage. For example, over here this is a non-return to 0 level, so called NRZ encoding. It uses two different voltage levels to represent zeros and ones. Typically negative voltage equal to 1 and positive voltage equal to 0, and the signal never returns to 0 voltage. So, it sort of flip flops between a negative between a negative voltage and a positive voltage. The value during a bit time is a level voltage. That means, during the duration of a bit 0 or 1, the voltage really remains the same. So, there is a transition at the boundaries of bit, and of course, if there are two ones, then there will be no transition, as we can see, or if there are two zeros consecutively, then there will be no transition. So, the number of transitions is much less, but of course, the and it is a very simple kind of scheme. This has some problem, okay, we will come to that later on, but let us look at now another variant of this non return to 0, which is says NRZI, that means non return to 0 and invert on ones. That means once again we keep constant voltage during bit time, no transition represents a 0 and transition from low to high or from high to low is a 1. So, the same bit pattern 0 0 1 1 0 1 is represented by a different voltage pattern over here. There is no transition 0 0 and then there is a 1. So, there is a transition, there is another 1, there is a transition 0, no transition, then again a 1, then another transition. Okay. So, this is another way of encoding. So, let us look at now the trouble with these encodings are that suppose you have a large number of zeros, large train of zeros, all right. So, if you have a large train of zeros, there is no transition really. Okay. By the way, just one point, the reason why they use a positive voltage and a negative voltage rather than a positive voltage and a 0 voltage or a 0 voltage and a negative voltage is that you want to distinguish between a 0 being sent and no signal being sent, all right. So, that is one point, and the other point is that, as I was saying, that if there is a constant train of 0 in the original data, then you will have a constant level signal in the system. Now, if that be so, the synchronization of the clocks between the sender and the receiver, that tend to drift off, okay. And when they drift off, then the receiver, I mean in the worst case the signal may go one off, or it may interpret the signal in a very wrong fashion. So, this is a problem of this NRZ or NRZI, which is taken care by some other kind of encoding. We will come to that later on. So, this is just a quick look at the disadvantages of NRZ code. Hard to tell where one bit ends or starts. With long strings of zeros or ones, any drift between timing of transmitter and receiver results in errors. So, there is a bit phase encoding which use at least one transition per bit time. So, if you use at least one transition per bit time, what would happen is that the sender and the receiver clocks can remain in very close synchronization with each other, and that is a nice property. So, and predictable bit transitions during each bit time. So, absence of a transition, so if there is an absence of a transition, that indicates an error. So, two examples are Manchester and differential Manchesters. So, this is Manchester encoding. So, you see that at the middle of each bit 0 or 1, there is a transition. Okay. Now, low to high transition means a 1 and high to low transition means a 0. So, the same pattern 0 0 1 1 0 1 is for each bit, there you will see that there is a transition in between, and low to high transition is 1 and high to low transition is a 0. Okay. So, this is the encoding which is used in Ethernets and many LANs. There is another variant of this called differential Manchester. So, in this the mid bit transmission is really for clock synchronization purpose. They do not represent either 0 or 1. So, what it does is that transition at the beginning of a bit period is equal to 0 and absence of a transition is a bit period 1. So, 0 0, so when this 0 starts, there is a transition. So, transition at the beginning of the bit period is a 0, but when the 1 starts, there is no transition. There is a transition in the middle anyway, that is for clocking purpose. Then at the next level, once again, if there is no transition, if there is a second one coming, there is no transition, and so on. Okay. This was used in token ring networks. Of course, token ring networks are becoming less popular these days, but anyway, this is another. So, there are other kinds of encoding techniques, but these are quite common ones. So, you see that there are different ways of encoding the digital data into these different signal levels. and signal levels, once again signal levels and bit rates, they are different. Signal level, the rate at which the signals change, the rate, that is the baud rate, and the rate at which bits are being sent, that is the bit rate. Now, the other is then the other thing we can consider is the analog encoding of analog information. Of course, this does not come too much into computer networks as such, but this is an important area in communication in general. So, of course, if you have an analog signal, I mean if you have a analog signal, it can directly be sent. Okay. Sometimes it is sent in the raw form, okay. Sometimes that is not very practical. So, we have to we usually sort of convert this to a analog signal, maybe at a higher frequency, and the most common example of this is the radio. For example, say radio is carrying voice or maybe some sound, etc. Now, the voice as you know is only 4 kilohertz, okay. But if you take a 4 kilohertz signal and try to send it over the atmosphere, it will not reach anywhere, okay. So, for the, I mean unless excepting the very near vicinity. So, in order to reach out to all these different locations, you have to send your radio signal at a very high frequency, but the information that it is carrying, it is still at that 4 kilohertz bandwidth. So, this 4 kilohertz bandwidth is sort of translated. So, there is a very high frequency so called carrier wave, which is carrying this 4 kilohertz of signal. If it is only voice, of course, if it is music, etc., etc., you may like to have a higher somewhat higher bandwidth also. But anyway, so that is also analog signal, this is also analog signal. So, one analog signal is carrying the other analog signal, and there are various ways of doing this so called modulation. The three most common ones are amplitude modulation, frequency modulation, and phase modulation. So, we will not talk much about this because amplitude modulation, as you can understand, the amplitude of the carrier wave is changed according to the signal. Similarly, in frequency modulation, the frequency of the carrier wave is changed according to the signal, and in PM the phase is changed according to the signal. So, this is another picture of digital signaling, the so called current state. That means 0 represents the low voltage, 1 is represented by the high voltage, and digital signaling and the state transition. So, if there is no transition, that is 0, if there is a transition, that is a 1. So, these are all different examples of encoding. As I was telling, that the bit rate and the baud rate are different, and the maximum number of times a signal can change in a second is called the baud rate. The number of bits, ones and zeros, transmitted in a second is called the bit rate. In the examples we have seen so far, the bit rate and baud rate are the same. This is not always the case. The bit rate can be higher than the baud rate if you use more than 2 signal levels, and the other one is also possible, that the bit rate may be lower than the baud rate, that is also possible. Now, let us look at some of the inherent trouble with all these physical media. That means, when we are throwing some signal, that means when we are trying to send some signal down some transmission medium, whatever it is, it may be a piece of wire, it may be this whole atmosphere ether, or it may be a fiber optic cable. There will be some kind of there will be some kind of distortion, some kind of change in the original signal, that will all inevitably come into play. So, we will just look at some of these. So, we have to really take care of all these. So, we have to design our system in such a manner, so that, for example, these signals, these kind of effects you cannot eliminate. Okay. They are basic properties of I mean the world is not perfect, and they are the basic properties of the medium. So, we will have to design our systems in such a way that in spite of all these effects, the whole communication will still go on very correctly. So, the one is that as signal propagates, signal changes as it travels. So, the receiver may not be able to recognize it as such. For example, this shows the example of an original signal and the final signal. So, now, this kind of change and distortion etc., may be attributed to the following effects. The first one, the very first one is attenuation. Signal gets weaker as it propagates. Attenuation becomes greater with distance naturally, and of course, finally the signal may become too weak to recognize. So, the original signal strength is something, but as the distance grows, the signal becomes weaker and weaker. For example, let us say, of course, this kind of weakening depends on the property of the medium. It also depends on the kind of frequency you are using for sending. For example, let us say an AM signal we will not get at a very large distance, whereas a short wave signal will travel some other way and come over here. Similarly, if you take a local area network on a cable, and if you make the cable very long, well, there are other technical problems of making the cable very long, but even from the signal propagation point of view, the signal will get weaker and weaker, because there will be leakage currents in the cable. So, current will leak out etc., etc., and finally, the signal that you will get will be very weak. So, this is a very fundamental property of any medium. Similarly, if you take an optical medium and if you send a light pulse through it, as it travels, the light pulse will get weaker. That is one of the effects. There are other effects, but this is one of the major effects. Apart from attenuation, the other thing is distortion. That means the signal changes shapes as it propagates. Now, if it changes shapes in this way, adjacent bits may overlap, may make recognition impossible for the receiver. So, what might happen is the signal changes shape. Now, why does it change the shape? If you remember, in the very beginning I had shown you one slide of a square wave kind, and we talked about some harmonics. So, the square wave may be looked upon as a sum of all these harmonics, sum of all these sine waves. Now, all these harmonics or the sine waves, they are at different frequencies. I was talking about sine x, sine 2x, sine 3x and so on. So, they are of different frequencies. Now, signals of different frequencies change or are affected by the medium differently. Okay. So, a signal of a particular frequency may be attenuated less, the signal at a much higher frequency may be attenuated much more, or vice versa, whatever. The point is that signals at different frequencies will get affected by the medium in a different ways. So, finally, the relative strengths of these different frequencies, they will be different when you go to the far end, that means when you go to the receiving end, and when you add that all this up, you will get a different shape. You will not get your old square shape or whatever shape you had sent, you will not get that back. So, this is called distortion. Then of course, it is going to pick up noise. There is a thermal energy in wire, so which is everywhere. So, this energy is some kind of an inherent noise that will always come. Then there will be random signals. So, spikes may sometime occur, say some car is starting somewhere. Okay. So, there will be some static discharge, there is a lightning strike somewhere. So, there is somebody is running a motor, somebody is running a washing machine. So, all these things add to the general noise in our atmosphere, and this medium which is carrying your signal, it will also catch some of this noise, and this and sometimes of course, the noise is so sharp that it may change the I mean transmission in such a manner, so that you will not get the original signal back. So, sometimes such a thing may happen. So, what we want is that we want a high signal to noise ratio. in order to distinguish between the signal and the noise. Now, if the noise is very low and the signal is high, we can still on the at the receiving end we can distinguish between this that what is a signal and what is a noise, and take the signal out, take out the noise. Okay. But if the signal, so for this we want a high signal to noise ratio. Signal strength divided by the average noise strength, that is the SNR, and as SNR falls, error will increase. So, in this figure you can see that as the signal becomes weaker and weaker and touches the noise floor, maybe goes below it. Now, when it goes below it, that means the noise has become more than the signal, then no meaningful communication can be carried out. So, in general we want a strong signal to noise ratio. So, one thing we might do quite often is that suppose we do have to send a signal to a very long distance. So, we want to have to send a signal to a very long distance, and the signal will naturally get weak. So, in between we will put some amplifiers or repeaters or regenerators, whatever you call them, which will take this signal, try to filter out the noise as much as possible, then amplify the signal, make it stronger, and then push it for the next span. So, after some distance, again another repeater will take it up, okay, and regenerate the signal. So, we have to go on doing that, so that I maintain an acceptable signal to noise ratio even at the receiving end. Then of course, as I said that there is interference, that means energy from outside the wire adds to signal like noise, often intermittent, so very hard to control or diagnose. Okay. And one important point is that in a very strong interference can occur at cable termination. Okay. So, there are two things. First of all, if two cables are running in parallel, what might happen is that the signal in one might affect the signal in the other. So, there is some kind of linkages between the two. So, this is called crosstalk, that is one thing. This is more pronounced at the termination end, and at the termination end, if you do not terminate the thing properly, if you just leave it like this, then the kind of distortion and the kind of noise that will introduce will be much more. So, whenever we are putting some wired kind of network infrastructure, we have to be very careful about the termination, because that is where a lot of noise can come in. So, often there will be multiple wires in a bundle, each radiates some of its signal, causes interference in nearby wires, and this is especially bad at terminations where wires are unwound and are parallel. Okay. So, this is a special case. And finally, I just mentioned this, I have already mentioned this earlier, that when carrying digital data over analog lines, we require modems. Okay. So, we require so this is modem stands for modulation and demodulation. This is used to connect a digital computer to an analog phone system usually, okay, but modems can also be used elsewhere, can be installed internally or a card inserted into the motherboard, or can be connected to the serial port, etc. So, now we understand why modems are required, because essentially digital data will have to be carried on the analog system. Okay. So, so we have had, I mean, of course, the field of communication, as you know, is a very interesting field, and we could not go too much into the details of communication, but this is we have just talked about the very basic of communications that is used in computer networks, because once again remember, a computer network has some computers or some network nodes connected via some communication lines. So, communication is absolutely important, all important in this. So, we have talked about this. In the next lecture, we will look at some of the medium that is actually used or deployed in common networks. Thank you. Good day. So, today we will have the second lecture on the physical medium. In the last lecture, we have seen the different ways this digital signals and analog signals etc., how they can be used for communication, how digital data or analog data can be encoded into, well, we are mostly interested in the digital form of data. So, how they can be encoded etc., and some of the general impairments of a physical medium we have seen. In this lecture, we are going to look at specific media which are used in networking. Okay. So, there are basically two types of media which are used for communication. One is cable. I mean, there are two different classes altogether. So, one is a cable. Now, this cable could be some copper cable, they could be coaxial cable or twisted pair or shielded twisted pair. So, the twisted pair, I mean, we sometimes they are actually unshielded twisted pair or UTP. Sometimes we simply call them twisted pairs since they are more common. There are shielded twisted pairs also. And then of course, one of the most important cables these days is the fiber optic. So, these are the different types of cables that we use in networks. Similarly, we can also communicate without the use of any cable by simple electromagnetic radiation, and this radiation could be in different ranges of the frequencies, like they could be infrared or microwave or radio or satellite etc. So, we will look at all these one by one. First, let us look at the kind of media that we use in a LAN. LAN, as you would remember, is a local area network, and a local area network could vary from, let us say, 1 meter to 1 kilometer. So, it is local strictly by some means of its size in some way. So, 1 meter means 2 computers connected residing on the same table, connected side by side. It could be all the computers in one building and all the computers in several buildings and so on. So, that is a kind of range that we have for LAN, and the medium that we use for a LAN, they could be coaxial cables, UTP, fibers, wireless. So, you would note that basically most of the types of cables that we talked about find their way in some niche or other in local area networks. And of course, UTP or unshielded twisted pairs are of different varieties, so or categories. So, that CAT is for categories. So, we could have CAT 3 cable, CAT 5 cable, CAT 5E cable, CAT 6 cable, CAT 7 cable and so on. You must have seen CAT 3 cable if you have looked. All your telephones, that means the landline phones, they are connected by unshielded twisted pair cables of category 3, all right. For computer networking, I mean, CAT 3 cables could also be used for LAN, although we usually prefer CAT 5 onwards. And the kind of things that are on the network, that could be your PBX. PBX is your local telephone exchange, that could also have some digital ports etc. Ethernet is one technology which is used in LAN. ATM is also used. FDDI is sometimes used. FDDI, if you remember, is fiber distributed, that is that FDDI ring kind of structure. Of course, there are some networks which are even smaller than a LAN. Okay, they are called personal area networks. Some networks. So, I may be wearing 3 or 4 computers and they are connected in a network on my body. Okay. So, we will come to PAN later on, but going on the other side of the spectrum, that means from LAN to a bigger network, which is a MAN, that is a metropolitan area network. Typically one campus or one city, maybe several small towns which are close together, they would come under the purview of a MAN. So, MAN would show a very rough ballpark figure is, say, MAN would be extend maybe about 10 kilometers. So, it could be 5 kilometers, it could be 20 kilometers. So, something in that range. And the kind of medium that we use for metropolitan area networks are coaxial cables, both baseband and broadband. We will come to these what they are. Once again, sometimes UTP are used, but that is not very preferred way of connecting, although UTP are used. One way where UTP is definitely used are when you try to network through telephone lines. That is I mean telephone lines, as I told you, they use UTP. It could be a hybrid kind of system. Okay, some part of it could be coaxial, some part of it could be UTP, and some part of it could be fiber. Okay, fiber means fiber optic cables. And the kind of things of course that the kind of technology that goes into a MAN would be PBX, different kinds of modems. For example, if you are using a broadband coaxial cable, you might use something what is known as a cable modem. Then you have this long reach Ethernet, that means Ethernet on the over maybe some lines, cable TV, DSL, digital subscriber lines, or it could be wireless. One issue which is important in MAN is the issue of access. All right, that means how do you reach to each individual users. I mean think of a town or a city. So you really have to, in order to network the entire town, you have to reach to each individual residence, and reaching to each individual residence involves cost. Okay. If it is a small building like in a LAN, you can take very good say UTP cable to his room. Okay. Now there are problems of taking UTP cables to each individual house. I mean there could be electromagnetic disturbance and things like that, but apart from that there is a question of cost. Okay. If you are trying to build so much copper into it, that is quite costly. So how to access to users who are distributed over a somewhat wide area in the sense of several kilometers, that is an issue in metropolitan area networks. And finally, at the extreme of the spectrum we have WAN, that is wide area network. So they may stretch from 10 kilometers to maybe 10,000 kilometers. Okay. So 10,000 kilometers or almost to the other side of the globe. So they may involve very, very long distance. Medium is usually fiber or satellite, and the kind of technology that is used in WAN are SONET or SDH. They are the almost similar technology. ATM, IP, that is the Internet Protocol, DWDM, dense wavelength division multiplexing, GEO and LEO. GEO stands for geostationary satellite, is a short form of geostationary satellite, and LEO is low earth orbiting satellite. So